My name is Eren Memiş Yazıcı, and I'm a senior research specialist at VTTI for the Division of Vehicle Driver and System Safety here at Virginia Tech. We appreciate you joining the webinar on the active inference models of perception and control. You have all come into the meeting muted and with your cameras disabled. If you have questions during the presentation, please use the chat box at the bottom of your Zoom window. We will address those questions either during the Q&A session at the end. If you would rather ask your questions yourself, you are most welcome to do that. You can either raise your hand and let me know, or you can wait, as I said, for the Q&A session at the end. Captions will be on for your convenience. At this time, I would like to introduce our presenter today. Dr. Alfredo Garcia received his Bachelor of Science in Electrical Engineering from the Universidad de los Andes in Colombia in 1991, DEA in Automatique and Informatique Industrielle from the Université Paul Sabatier in Toulouse, France in 1992, and PhD in Industrial and Operations Engineering from the University of Michigan in 1997. From 1998 to 2000, he served as a commissioner in the Colombian Energy Regulatory Commission. And from 2001 to 2017, he was a member of the faculty at the University of Virginia and the University of Florida. He currently holds the Mike and Sugar Bonds Endowed Professorship with Industrial and Systems Engineering departments at Texas A&M University. During 2016 to 17, he served as a program manager for the Multi-Agent Network Control Program with the Army Research Office at Research Triangle Park. And his research interests include game theory and dynamic optimization with applications in electricity and communication networks. At this time, I'm going to turn it over to him. And we are good.
All right. Okay. Thank you, Eren. So thank you for attending this talk. As Eren indicated, I'm not quite in transportation, but this whole project started out of a collaboration with Anthony McDonald, who's now at Wisconsin. And he was the PI in this project. And this is the work of Ran Wei, who's a PhD student and recently graduated and is now with this AI company Versus. And we have also collaborated with Gustav Markula from Leeds University and Johan Engstrom and Matthew O'Kelly from Waymo. So I like to start from the end, if you will, because I like to motivate the talk, which is going to be a little bit technical. But I like to show you what is the end product of a lot of the work that we did. So I like to call your attention to the two columns on the left. So what we have here, the first column is the data for task following in this data set, in the interaction data set. So we selected a subset of the interaction data set for this task following maneuver. And what you see here, for instance, is the different visualizations of the data. So you have relative distance to the car ahead, relative velocity and relative distance. And in the color coding is acceleration. So the redder, or the higher the acceleration, and so on and so forth. This is another part of the data. This is looming. So the rate of closing, the perceptual rate of closing to the vehicle ahead of you. And this is the inverse of that. So it's 1/seconds. And again, versus relative distance. And again, the color coding has to do with acceleration. And finally, the same variable in the y-axis and in the x-axis, we have the relative velocity with respect to the car ahead. And as I said, this is the color coding. So a negative acceleration, slamming on the brakes is a red, hot red, and then slamming the accelerator pedal is deep green, so on and so forth. So this is the data, and then in the column right next to it is what our model, at the end of all these comings and goings, we built a model, and then now we simulate the model. And this gives us a sense of how good is the model at the end of the day. As you can see, it captures some of the trends. It is unable to, capture this behavior that is kind of not as well represented in the data set. But for the most part, this visual sanity check tells us that this model that we're about to describe does a fairly decent job at fitting the data. So what is the model? And these are the two columns on the right. So the model, and this is the main point of our work, is a model that is structured into two parts. It has one part that has to do with perception, and that's this column. And as you can see, there is a color coding of the data. So what we have is a finite set of states that are associated with a collection of observations. So for instance, these observations here in light blue have to do with values of relative velocity that are high and values of relative distance that are low, right? So this is a light blue state compared to a deep blue state, which is one in which there are very low negative relative velocity values and very low relative distance values. So I will explain this in a moment, but what I'm trying to start out with is giving you a sense of what the structure of the model is. So there's first a part of the model that is dealing with perception, how the human agent takes the external sensory input and in a sense constructs a simplified representation by means of these hidden states. Notice that it has a flavor of categorical perception because a whole collection of sensory observations that are real numbers are kind of mapped into a color, right? So it's in a sense capturing a notion of categorical perception. And on the right-hand side, we have a model of preferences. So why are people doing what they're doing? It's in essence what this tries to explain. And the way to do it is to use a model of preferences. What is it that people like about when they're doing this task following maneuver? And so the colors are in the deep purple to extremely this light. So it's going to be in terms of a preferred distribution of observations. So what we're going to come out after the estimation exercise is a distribution of what the agents would like to see in the world. What is the distribution of the preferred observations? And so that's why it's a log of the preference distribution. And as you can see, these values here, where the relative velocity is high and the relative distance is low, these are values that are not liked. Right? They're very low log of the probability because these are dangerous, potentially dangerous situations, right? Instead, the values that have the highest preferences are values in which the relative velocity is close to zero, right? So hence the light color here. And also a distance that varies, let's say, according to a certain range. You can also see that there's kind of an asymmetry between the preferences for this type of observations as opposed to this type of observations. You know, the color, the intensity of the color is not the same. So in a sense, what we have built is a model of the policy that these agents are following. This is a population model. by means of constructing a perception model and a model of preferences. And this is what I would like to describe in a moment. So this is the outline for the talk. What are the basis of modeling a perception and control? How do we learn a model once we posit a model? How do we incorporate this notion of active inference, which is a fairly relatively new and very popular paradigm from cognitive science, and then the details of the application to the car following task. Okay, so modeling perception and control. So this is what I was referring to earlier as to what do I mean by saying when I say that the agent takes high dimensional observations and has a low dimensional representation of that. So these are the things in green are the things that we observe. I'm sorry, in gray. We also observe the maneuvers, right, that they are doing, the accelerations. And the agent internal representation is this bubble here. So this bubble here is essentially composed of, there is a hidden state, S, and there is also a belief about what is the distribution of the states. What is it? How likely is it that you are in a given state at a given point in time? This is this sequence of Bs, right? So this is the subjective representation of the world, of the environment by the agent. This is all these arcs have to do with parts of this model. For instance, this arc here, right? These arcs are essentially associated to a generative model of observations, meaning that the agent expects a certain type of distribution over the observations when the agent believes the state of the system is a certain value st. So this is these links here that in a similar manner, there are these beliefs about the state. So this is the belief that the current state, what is the distribution of the current state, right? And what we're going to use a Bayesian framework. So we're going to use beliefs as the conditional probability given the history of what has transpired after up to time t. What is the conditional probability of the hidden state is S, and this is our belief distribution. And finally, there is also a model of the state dynamics. So the agent also has a model of how the state of the world would change when undertaking a certain course of action, right? And this is a model by a transition probability. It's a Markovian model at the end of the day. And so our model of how the control actually exercises or has an effect in the state of the world is given by this Markov transition probabilities. So this is what people refer to, for those of you who may not be familiar, a partially observable Markov decision process. This is a POMDP, which is a model that is used in control, artificial intelligence. But in this case, we're using it as a representation of human agents' perception and action loop. Okay, so what are the ingredients of this POMDP model? We have a history of what has transpired in the form of observations and actions. And then we are positing the following rationale for what the agent is doing. The agent has some way of determining which are good outcomes or which are good states to be in and which are bad states. And this is the reward function R of ST over AT. So this is just a representation of the preferences of the agent in terms of the hidden states and the actual actions that the agent can undertake. And if we were positing this problem in terms of an unbounded horizon, that's why this sum is unbounded, we would have to take all these rewards and aggregate them into a single number, right? And this is why we use this discounting factor. But as we will see in a moment, we didn't have to use that in the task following because we're using a rolling or receding horizon paradigm. Now, there is this element that may not be familiar with some of you, which is there is an information processing cost. In other words, these agents have opportunity cost for how engaged they are in the task, right? So marshalling resources to undertake the task, mental resources, has an opportunity cost. And so if you are busy doing something else, like you shouldn't be, like texting or talking to somebody else, this opportunity cost, this C, is a measure of what are the information processing costs. So how focused on the task or how costly it is to fully engage in the task. Okay, so these are the primitives of the model. And as I said before, we're going to be taking a Bayesian approach to modeling the way the agent sees the world. I will need to kind of formalize the elements of the model. Two more definitions. One is the Specter Reward. And notice this expectation is with respect to subjective beliefs, right? So this is what I believe my reward would be if I were to implement action AT when my beliefs about the hidden state of the world is B of T. And then this is also what I expect the observations will be, right? So in taking action AT, when I believe the state of the world distribution is BT, this sigma is a distribution over observation. So it's telling me what is it that you expect the observations to look like when you do this control action, right? And so on the basis of these two things, for those of you who are familiar with the dynamic programming formulation, this problem can be expressed in a recursive fashion. So we can use this device called the value function, right? So it's a function of the current set of beliefs. And I'm going to use B star to denote that this is the optimal value function. And it happens to have this recursive structure. So you do what is the value of what you're supposed to do best is the maximum over all the possible policies that you can consider at this point, and they will give you this immediate expected reward, plus the future reward, which is a function of which observations you're likely to see, right? And the resulting beliefs that you are going to construct on the basis of those observations that you are likely to observe, right? So this is a very nice mathematical characterization that allows us to do a lot of computation. Okay, now we are going to work with the following specification for the information processing cost. So information processing cost is going to turn out to be something like a distance, right? This KL divergence is not quite a metric, it's not quite a distance, but it's close to a distance between two distributions. And so what we have is that the agent has a default policy, so it has learned to do this task after training, so it has a default policy. But of course, if fully focused on the task, that agent may actually do even better. So we're gonna, by using this specification, what we're saying is that the finer the agent is in undertaking the task, the costlier it is for the agent, right? So the agent can do little effort and just revert to the default way in which the agent does things. Like, this is how I learn it by from memory, and I just will do things, in a mechanic way. But that will be when this cost is high, then maybe you want to revert to the simpler way, the default control policy. But if you want to really dedicate your resources, your mind resources, to identifying which is the best course of action, then there will be you will identify a policy pi that will be different from this default, and the measure of this distance between these two distributions is a proxy for information processing cost. So the nice thing about this specification is that it gives us a closed form expression for the optimal policy. Right? It's in the form of a softmax policy. This simply says that the likelihood that I take action A when the beliefs are B is going to be this is proportional to how big is this value Q, right? And this value Q is the immediate reward that I would receive by undertaking action A when in state B, plus the future reward, which is the expected value over all possible observations that and the likelihood that I will see this O prime, and then the resulting beliefs that I would be in at that point on, right? So notice that this is kind of like a bias. This default policy serves, in a sense, to capture the default way of doing things is already there in the background. And then, depending upon how high is this cost, you're going to improve upon it by your optimizing behavior. Okay, so this is a model of both perception and control. This is the actual control policy, which is determined by basically the two parts of our model are going to be this guy here, which are the preferences, right? And this guy here, which is the perception. How is the agent expecting things to change in the environment as a function of the actions? So that's a lot of a very short description of this POMDP model. Now we take we change hats and take on the statistician hat. And we have data. And what we would like to see is which of these POMD models would be the best fit to our data. So this is the question of learning a model of perception and control. So now the problem is I have data in the form of sequences of observations and implemented actions. And I'm going to call that, let's say, tau. And so when we have this interaction data set that is like a video of from high up of the cars engaged in the highway in a task that is car following, right? We are not dealing here with merging or with exiting or entering the highway, right? These are other tasks. We're only dealing here with the tasks associated with car following. And if we have this video from up above that gives us the relative velocities, accelerations, distance, and all you name it, then what we have is a sequences of observations and implemented actions. And what we like to see is how do we go back from the data to a model, right, that identifies the primitives of perception and control. And as I said, the primitives are going to be in the form of the reward, the preferences. How good is an action when a given set of beliefs is given, and what are the expectations about the way the world is going to change as a function of the action undertaken, right? So in another word, this is what I have in the next slide. So I have parameter θ1 for my model of perception. So I need to estimate θ1, and by that I mean a Markovian transition kernel for the state, the hidden state, and observation probabilities for the actual observations O. And then a model of preferences, which is a simple reward function, right? So this is the model. And well, I like to choose these values of θ1 and θ2, so that they are close to give me a high likelihood, right? So the log likelihood will be essentially the probability that I observe when I specify the values of θ1 and θ2. In this POMDP formulation, I have specified essentially what is the optimal policy. And so by changing the parameters, I am playing with different specifications of the optimal policy, right? And so this is the log likelihood of the data given a choice of the parameters, which are, as I mentioned a moment ago, the parameters for preferences, reward, and environment dynamics, the transition probabilities. Okay, so this turns out to be, so now if we let me stop here for a moment and say the following. This is this is not an easy problem to solve, because you can imagine that when an agent is executing or planning a task, a control task, there are trade-offs over time that are being considered. Right? So how do you evaluate trade-offs over time? You have to have both a model of rewards, but also a model of how is the environment going to change. So if you're trying to find a model that rationalizes data, it could be that there might be multiple ways, multiple combinations of reward and models of the world that are going to be consistent with the data. In other words, this problem is not identifiable, right? In general, as it is, there might be many models that are consistent with the same data set. That poses a big problem for us, right? Because this is what we would like to see, is to go back from the data to a model. So to alleviate this non-identifiability, we're going to make an assumption that is essentially, this is the mathematical description, but in words, it says the following. The agent is sufficiently good at the task. In other words, I'm going to have, remember that I parameterize with theta 1 everything that has to do with perception of the environment. And so by saying that the prior on theta 1 is increasing in the likelihood of the observations, so this is the likelihood of observations. Right? Remember that delta is this way that we parameterize the distribution of observables as a function of the current beliefs and the actions. And so if an agent is an expert, this means that this agent has a fairly accurate model of the environment, right? And this parameter, this is a hyperparameter, unfortunately, but we have to pay the price. Lambda gives us a way to control how accurate is the model of the environment that this agent has. And so we'll start with this assumption, and then we can put together now what is the log of the posterior distribution, right? So since we're interested is in the posterior, given the data, what is the posterior distribution? Then we find that under this assumption, the posterior distribution will be proportional to the log likelihood of the actions that are in the data set, plus this log likelihood of observations, which are multiplied by this accuracy hyperparameter that essentially allows us to describe how accurate we believe the model of the environment that the agent has is. Right? And so at the end of the day, this is our objective. Our objective will be to try to find the value of theta that maximizes this posterior distribution. Right? And this is our, it all boils down, the estimation problem boils down to solving this bi-level optimization problem. So why is it bi-level? Because, okay, we have an objective which is to find the maximum a posteriori value of theta. So we now have a sense of what is the posterior distribution of theta, and we would like to find the maximum value of that posterior distribution, right? MAP estimate, that's the objective. But we would like to do so, but all the while keeping in close sight the fact that this is a rational agent. This is an agent that is behaving according to the tenets of this model, which is maximizing some rewards that are a function of preferences, and it has an information processing cost. It's paying attention to a level, to a certain degree. Okay, so this is the actual technique, right? Okay, so now let me move ahead and tell you a little bit about active inference, because this is from up to this point, what I have done is I started by positing the PMDP model, which is a general description of acting under uncertainty, under partial observable states. Then we consider the statistician problem, which is, okay, I have data, I want to see which is the PMDP model that fits best the data. And now we would like to see if the state of the art in cognitive science allows us to make a more appropriate choice or specification of this model. And this is where active inference comes into play. So let me do a quick overview of what I think is active inference. So there's a recent textbook, and this is I'm doing market MIT Press by Carl Friston and his colleagues on active inference. And so the idea of active inference is that unlike other paradigms of cognition, which are essentially posited on the premise that the brain is like a prediction machine, we're constantly trying to predict what is going to happen next, right? That this inference is not just passive, it's not just the world sending us, inundating us with sensory input, and us trying to figure out how is the world, but also we are active in the world. We act in the world, and we act in the world so as to induce a distribution of observables that is according to our desires, right? So we want to match what is perceived versus what is preferred, right? And this is why the term active, because the brain is not passive. The brain is also actively engaged in the world, trying to change the distribution of observables in a certain direction. So this is a typical plot that they use. So we have, this is the world, right, with observations, and we are here, it's a human brain, but the human can also act upon the world so as to change the states of sensory data. And what is appealing about active inference is that these two things, you know, both this loop here and this loop can be seen as the two sides of the same coin. And that coin is essentially free energy. So all the brain is doing is minimizing free energy. And why do they mean by free energy? Is a measure of surprise. So for instance, here, when I'm trying to build a model of what I think the world is like, I am trying to minimize surprise. I don't want to believe in a world that then would be totally off with respect to incoming data. I want to minimize surprise. And lo and behold, a Bayesian brain will be one that will do a very good job at not being surprised by the environment. But there is another side of the coin, which is this active part, right? So in this active part, then the agent is acting so as to minimize surprise in the form of I want to see observations that are in accordance or close to a certain preferred distribution over the states of the world. Right? So this is, I mean, in the time I have tried to explain the general underpinnings of this very appealing theory. Now, what we did at the end of the day, right? It's a simplification, is we simply take a specification for reward in terms of negative expected free energy, right? So there are two parts to this. There is a first part, which is usually referred to as pragmatic value. And so in a sense, this is where the preferences of the world are playing a role. What this is saying is, I would like to make sure that what I believe about the state of the world matches what is my preferred distribution about the state of the world, right? So this first part can be seen as a pragmatic value, that's the term they use, to refer to the fact that I like the states of the world to be according to P tilde, and I would like to make sure to minimize this mismatch between what I believe, what my beliefs will be after I take this action, and the distribution of the world. But there is also a very important second component, and this they refer to as epistemic value. And this means, in addition to pragmatic value, I'm also concerned about being in states of the world in which I'm likely to be surprised. There's a lot of variation, or a lot of entropy. So this term here is the entropy of the model of the world, of the observations that results after taking action AT and landing on a state ST+1. So in addition to being close to what I like to be in, I also dislike being in states for which I have very little certainty as to what are the observations that I should expect, right? And this second term is called epistemic value. Sometimes the agent under these preferences would be justified in taking an action that doesn't seem to be all that rational from the point of view of preferences with respect to states of the world, but that one action might mitigate or minimize the uncertainty as to the distribution on the states of the world. This is the nice balance between you have a goal, but you also have limited knowledge about the way the world works. And so sometimes you might be better off by just simply staying put with a situation in which your uncertainty about the state of the world is not as high, rather than shooting for a presumably high pragmatic value, but with a lot of uncertainty. Okay, so this is the specification that we did for the model. And now we go to the actual, I think this is what you guys are interested, because this is a transportation talk. And so we did a very simple, this is a simple task, car following. Nonetheless, it has its own set of complexities. Okay, so we use the interaction data set. And from that data set, we took, by the way, those who are interested in the details can click here. This is we have a report on the archive with the details about this work. Okay, so so we take the interaction data set and we selected a number of trajectories in terms of position, velocities, and headings, at a sampling frequency of 10 hertz, right? So these are like videos of these cars that are following the task. So this is a picture of that. And there are cars that are going in one direction, and there are cars that are going in another direction. And these lanes, the going from east to west, west to east, may differ in the traffic, the average speed, and things like that. So this is a good way of testing. You will see later on, of testing how much of a generalization capability has the model, because we can train a model in one sense and then use it in the other sense to see how good does it do. Okay, so let me start with what are the alternatives. So we used a specification of the intelligent driver model, which is an engineering model that specifies a certain number of parameters. So it's a very transparent model, because it's purely dictated by a system of equations, right? And the dynamic equations are governed by a few parameters, and then all we're doing is playing with the parameters to see which one fits the best the data. Then we consider two machine learning models. And so machine learning models are essentially black boxes. In this case, this is just a multi-layer perceptron, just a neural network. And so what we do is we don't know what is going on inside. This is the total opposite from IDM, whereas IDM is completely transparent, right? These two guys are completely not transparent, because these are black boxes. We throw data in, and we do this supervised training by means of this technique called behavioral cloning. So in behavioral cloning, all you do is to try to maximize the fit of the data by using this either a multi-layer perceptron or a recurrent neural network specification. Okay, so in the first set of evaluation that we conducted, we refer to this as offline, because all we're interested is in how good of a prediction is our model doing. And we refer to the model as AIDA, so it's an active inference driver agent. And so how good of a prediction in terms of the acceleration, right? So in car following, all you're doing is essentially slamming on the pedal or on the brakes. And we would like to get a sense of, relatively with respect to these other models, how good of a job the active inference is in predicting the acceleration and our braking patterns in the data. And so it does a very good job. This is the performance. Now notice that the performance metric, this is the mean absolute error, but we are using the interquartile measure. So we're dismissing the extreme quartiles of the distribution and taking the mean absolute error over those remaining values. And again, the comparison is done with a different lane, right? So we do the same lane testing and then the different lane testing. And this we call offline evaluation, right? So the offline evaluation, things are looking good. Things are not as good, but continue to be relatively decent in what we call the online evaluation, right? So here, the objective is a little bit different. We're not interested in how good of a fit or a predictor we have for acceleration, but rather how good of a control we have been able to extract from this data. So what we do is we take the controller, the policy that we were able to estimate, and we plug it to a real simulation of the environment, right? So the controller is just going to, that's why it's referred to as online. It would be put in the closed feedback loop with the environment, right? And so as you can see, and the measure of performance is the deviation. So this is absolute deviation with respect to the actual the car ahead. I'm sorry, the original performance. And so we start to see that here it's not so clear anymore that AIDA has the best performance, even though it's still competitive with the multi-layer perceptron model. But mind you, we still have it's still doing much better than the IDM model, and it's giving us a sense of these primitives of the model that are highly interpretable, as I started the discussion a moment ago. Okay, so another way to see the performance is if we track a trajectory. So this is relative distance, this is relative velocity, and this is looming, right? And see the performance of the agent. This is the true acceleration, right? On the right-hand side, we have the true acceleration. So this is a very sudden deceleration, followed by then an acceleration. And we would like to see in this kind of particular sequence how good the model does. Now, maybe this is not so clear to you guys here because this is in gray, but remember that these are random policies. And so it doesn't give us, it's not going to give us a value, but it gives us a distribution of their actions, right? But what this is saying is that most of the weight is on the actions that you can see here that are kind of mimicking the actual data, and then likewise for acceleration, okay? Now, as for the hidden states, so this is the belief distribution.
Dr. Garcia, I just wanted to remind that we have 5 minutes remaining.
5 minutes, yeah, I'm about to finish, yes. And so the belief distribution, remember, these states are this construct that the model comes up with that are associated with a categorical description of the environment, right? And so typically you have states, these states are maybe dangerous states, right? And so the belief is that you are in a dangerous state, and then you go back once you accelerate to a relatively normal state. Okay, so let me finish by pointing out the limitations of this. The limitations are basically the data, right? And so one thing we observed is that when we do the online simulation, there might be crashes, right? So we take the model, we plug it into a real environment, and lo and behold, sometimes the controller leads to a crash. This is a situation of a crash, which is represented here by 2 vehicles being on the same location at the same time, right? Now, what we think is happening here is that there is a limit to how much we can generalize the model that we have built, because there are no accidents in the data set. There's very few observations of very tight or close to collision situations. And so, not surprisingly, the model that we are able to construct, which is a model based on normal operating conditions, it's unable to control a vehicle that is being subject to a very extreme condition in which, let's say, the looming decreases so rapidly to this value. So we do see these limits to the generalization. Okay, so let me conclude with a few thoughts. We have taken a long journey into using tools from stochastic control, statistical learning, and cognitive science to come up with a model that has a structure. Right? What we're doing here is saying we don't take a black box approach to modeling driving. We are able to identify the primitives on a model that is easier to understand. It's a bit more transparent than and that at least in this task, this is not done at the expense of effectiveness as a model, right? Because typically these machine learning models are going to outperform anybody because they are massive and they have billions of parameters and they will do a much better job, but at the expense of lack of transparency. So at least here we are always making sure that we have an interpretable model within sight, rather than making a leap in the dark and letting the machine learning identify something that we don't really understand how it's working. And this is, I think, what the merit of our work is. Now, for future work, we would like to, and there is evidence in the data set that there is heterogeneity, right? So this is an important part that we kind of run out of time. And by that, I mean that not all drivers, a population model only goes so far, because you can see that there are drivers that are more aggressive and there are drivers that are less aggressive. And it would have been nice to also build like two different models for the same data set, in which one is associated with some fraction of the data set that is associated with drivers that we believe are more aggressive, people that have preferences for being closer to the car ahead, or other drivers that are more conservative and don't do that. But this is a part of the work that we were unable to complete. And so with that, I close, Aaron. Thank you.
Thank you so much, Dr. Garcia. At this time, we welcome any questions, or if anybody has any questions, please go ahead and use the chat box to go ahead and read them. While that is something that people may be mulling over, I did have a few questions that I'd like to ask.
Okay, sure, go ahead.
How scalable is the estimation method that you're saying?
That's a very good question. Okay, so there is a lot of computation, and the bottleneck probably is in this. Let me go back to the slides. Okay, so if you remember, the heart of the estimation is solving this bi-level optimization problem here. Oops, sorry, here, right? So this part, the upper level problem, is relatively easier. We're doing stochastic gradient updates. The harder part, the part where it's not easily scalable, is the inner loop, right? Because in the inner loop, we're solving a stochastic dynamic programming problem. This is where the receding horizon, I forgot to mention this, but there's so much information that I can put in the talk. But our model of the agent is an agent that is looking ahead h units of time and deciding what to do now, and then revisiting that decision. This looking ahead h units, it's solving a POMDP, right, with the computational burden that entails. And so the scalability maybe the bottleneck may lie in this inner loop, which for the purposes of our task following environment was not, because it was a simplified environment. But if we were to take this to a more complex environment, I'm sure this would be a bottleneck.
Thank you. Another one that we have is what is different and or unique about the active inference?
That's a very good question. Yes, I think it's twofold. The answer, in my opinion, right, is that it's a nice encompassing framework. So as I described, it puts in the same token this and this loops, right? So this is the estimation, and this is the control, right? And typically, there's been like in the control literature, there's been literature on the duality between these two tasks. But active inference does a very nice job of putting these two things as two sides of the same coin. And in particular, I think what many models don't have is this emphasis on the epistemic value, right? So whereas you all have heard exploration versus exploitation in sequential dynamic decision making when the environment is unknown, and then there is a merit in exploring before you actually exploit. But I don't think that there is such a compact and analytically workable representation as the one that they are giving in this sense, because it essentially is all in the same currency, if you will. It's all in the you're estimating distributions, right? You're making actions so as to induce distributions, and that facilitates looking at both the backward and the forward problems in the same type of perspective. So I think what is novel is the fact that it encompasses in a nice way the two problems, and that it highlights the importance of the epistemic value in human decision making in dynamic tasks.
Thank you.
Oh, I have to say also that there is evidence of this is a topic I'm not familiar with, but I think there is evidence like neural footprints of a lot of the theories that underlie active inference. So there is evidence that our brain works the way this way, and the way they conceptualize this active inference framework. There's a question of, do you think the model is region specific or can it be generalized globally? This is a good question that I think is also related to heterogeneity, right? So in a sense, so I think that the key point here is heterogeneity. If this data, so we ended up only working with data from China, even though the interaction data set has entries from other countries. But it was a means to try to control. We cannot deal with too much heterogeneity, right? And so in the next step, what we're planning to do is to try to enlarge a little bit this model by using expectation maximization to be able to account for heterogeneity. In other words, the answer would not be, this is your model, but this is a collection of models that are can be used to describe this data set. And this is something that we haven't done yet, but I think it might be worthwhile looking into. Thank you for the question.
Thank you. I'd like to thank everyone again for joining the webinar. This webinar will be uploaded to YouTube, and we will notify everyone via email when it is complete. The registration is open for our next webinar. The next webinar will be on the real-time risk prediction at signalized intersection using graph neural networks, presented by researchers at the Virginia Tech Transportation Institute. This webinar is scheduled for October 24th at 2:30 Eastern Time. You can register now with the link that I will send over to the chat window. I will leave this up for a little bit if everyone would like to register for the next webinar. And thank you all so much again for attending. And thank you, Dr. Garcia, again for your presentation today.
All right, thank you.